got that. All right, I apologize that I showed up late. I was at the wrong venue, apparently. Um, Thank you for joining the session. I know I'm in the way of some of you to grab your lunches, so I hope we'll make it exciting. My name is Alan Turletto. I'm the field CTO at Redis. I've been in the in-memory database slash NoSQL space for over a decade, and through that time, I've watched the market mature, go through different iterations of hype cycles, and I want to connect a few things for you today that talk directly to the convergence that we're seeing in the data platform market and tie that into what we're seeing in terms of the new hype cycle around generative AI and how that connects to vector databases. All right, so we'll jump in. So a quick prelude, we all know this, but we're heading towards a digital-first economy. So of course with COVID, some analysts say we accelerated that by about 10 years. And what that means is effectively that really industry agnostic, most of the businesses today, primarily their front door is a digital. So whether you're thinking about the way you bank today, banking, the way you interact with your retail store, or maybe your kids are still gaming and they're not gaming on consoles anymore, it's these big multiplayer, huge virtual type games. All of it is through digital interactions. Now, if you think about the implications of that onto databases, think about your experience in the store. You go, you try on one shirt, another shirt. Maybe you finally make a purchase that takes you 20 minutes. But as a database, there's only one interaction, right? It's the actual transaction of you purchasing that product. Now, apply that experience to the digital, where you might be looking at different products. I see people on their commutes, and they could spend a whole hour just kind of going through different product catalogs. And every one of those is a new operation on the database. So the volume has increased through the digital experience onto these kind of legacy databases, right? And it's not just transactions. We talk about the variety, more semi-structured and structured, because we want to leverage that information to be much more proactive about how we engage with that user base. So when we connect that back to kind of the maturation of the database market, and you take a step back and you think about where databases originated, a lot of them, when we talk about mainframes, oracles, they started in about 60, 50 years ago. Sometimes it's important to say that out loud to realize how long ago these databases were created. And listen, these are fantastic technologies. They're not going anywhere. I have a friendly kind of wager between myself and the mainframe about who's going to retire first. I'm pretty sure it's going to be me. But these technologies were created within a context. They were created at a time where the first principle was about reducing down the storage cost. If you've ever seen photos of what mainframes were back in the day, a lot of that was about the cost of storage. So when they built these databases, they built them with disk in mind. That was the cheapest storage of the time. And they wanted to reduce down the storage, ultimately, right? And then they thought about data access. Then they thought about performance. They created SQL as a secondary concern. Now, fast forward to the 2000s, when storage costs plummeted, specifically RAM, it became feasible to build what are now called distributed architectures, distributed databases. We were able to leverage much cheaper infrastructure. And with that mental model at the time, we can actually prioritize data access, we can actually prioritize performance. So we can start to build for the way that we want to use or store our data, and we want to build for performance, and then think about storage costs secondary. And that's really where we started seeing a lot of innovation within the database space. And of course, that only got accelerated as we went to the cloud. So what we saw is a lot of categories start to be established in the database market. If you think about MongoDB and why it became very popular, well, right around the time where MongoDB came out, there was a huge shift from XML over to JSON, so JavaScript Object Notation. And just about everybody was passing JSON into their UIs or within their application layer, and it just was easier, right, to reduce that friction and store that data as JSON as well. Not have to pay the extra transformation penalty of thinking about what that looks like in terms of the columns and rows. And of course, with everyone transitioning to JSON, MongoDB became very popular. Same goes for Redis. Redis uses sets and lists. It's a data structure store. So all those natural ways that we express our data, we use our data, we can actually store our data natively. So it broke what's called that impedance mismatch, which is the way that we store data and the way that we use data. And when we can kind of unify that, we start to see a lot of enablement in terms of performance. And that's what really matters when we talk about the digital experience. Make sure we have that great performance. And of course, event streaming, search, all these other kind of secondary concerns came around because we were able to use more of a semi-structured and unstructured data and be able to take advantage of it for analytics. So we started to see these distributed architectures. But then something happened in this space, and I'm sure a lot of you noticed it, but I'm going to try to connect some dots if you didn't realize what's happening. With this innovation and with a saturation in the market of these use cases, what came is a lot of competition and also a lot of cheap money. So I'm sure you've heard of this, right? There was low interest rates, a ton of venture capital money went towards these companies, and as these companies went IPO or even before that, there was a ton of pressure, if you're not from the space, on constantly delivering growth, right? 60%, 70%, over 100% growth year over year. And when you saturate the market with the most basic use cases within your silo or category, you start to have to think about what else can we do. So what we saw was a convergence. We started to see these kind of like purpose-built platforms start to do things that overlapped into other platforms. So when you see headlines like Confluent, where the CEO was at Kafka Summit, I believe it was 2019, and he said, I see a bit of a missing piece in the database market. We're thinking of data as static. We should be thinking of data as in motion. Confluent will now come out with this ksqlDB, where basically effectively you have an event streaming database. So a logging company, an event streaming company, was then trying to position as a database. At the same time, you saw databases like Cassandra and MongoDB start to position into event streaming market, right? They're saying, hey, you can use us for data processing. They're actually competing with Apache Flink here, but guess what? Confluent acquired an Apache Flink company. So you see this convergence that's happening. And it's not just those two companies, and it's not just streaming. You saw this with search. We saw this around JSON. You see these around these like use cases, right? And it's not just the NoSQL players, because there's a lot of pressure on Microsoft, who has SQL Server, and all these other companies to continue to drive growth. So if you noticed, ANSI 2023, the spec came out, and it included JSON. But ahead of that was some of these, Postgres included, some of these other relational databases were already supporting JSON. So you see a huge overlap there as well. And of course, Redis I'm from Redis. Redis, we've been ahead of the game when it comes to this for many, many years. So not only were we a multi-kind of data structure store, but what you might not know, and of course synonymous with caching and session stores, but what you might not know is we actually supported for many years already, about a decade, an ability to do secondary in-memory indexing on hashes and JSON. And what that does is allows you to do SQL-like querying. It allows you to do a full text search. We even now support a SQL interface, so if you want to use JDBC or ODBC, you can do that against Redis. That's not something when Redis first came out you were able to do, but of course that overlap happened. And I already mentioned we support JSON. There's also time series and probabilistic filters. So again, doing more with the same platform. Event streaming, Redis is actually known for messaging through its list, but we created a Streams API, in addition to triggers, functions, and a seamless way to do data integration. But much more relevant to this topic, and where I'll go from this point on, is our recent, we've been working on this for 2 years already, ability to do what's called vector semantic search or similarity search. You may have heard about this, right? You maybe have heard about it already at the conference. So being able to store vectors, being able to find similar vectors, even doing hybrid searches, so you can do a vector search in addition to scalars or even geospatial indexing. Do things like prompt caching and chat history. So really being able to enable a lot of what you're going to see in generative AI, and I'll touch into what that looks like. So just in case you haven't heard of vectors or vector databases, let's just to level set, what's a vector? So we talked a lot about transactional data, or structured data rather, but I didn't touch into semi-structured and unstructured. So when we have data sets around audio and PDFs and video, being able to search on those or search for those or segments of those becomes a huge challenge. We're back to storage costs as a constraint, and the ability to kind of process all that information really becomes a challenge as well. And that's where vector databases really make an impact. So what you can do is you can use a machine learning model to encode that particular modal, or audio, a text, a PDF, and basically shrink it down to a multi-dimensional array of numerics. And what that does is just creates, let's say a 10 gigabyte of video into something that's going to be a few kilobytes in a vector database. And then I could apply linear algebra, cosine similarity, some of these advanced machine learning models, to then look for other multi-dimensional arrays that are like the one that I actually just put into my database. So now what I can do is I could take that video, I could take that PDF, I could break it up into what's called chunks. I can convert those chunks in what's called vector embeddings, and I can very quickly, within milliseconds, be able to find other vectors within my vector database and then provide that to you as an output, and then you can translate that back into what you were trying to do. So if you look at the image there, if that gentleman is wearing a shirt and the pants, and I want to just click on the pants, and I was able to chunk out just what the pants look like, then I can look up on the vector database, find just the pants, and then provide metadata where you can go and purchase those pants and anything else that you might want to know, right? That's pretty powerful stuff when you think about it from a retail perspective. So how does this tie into generative AI, right? We got to talk about generative AI at this conference, of course, with the hype. Well, you can do what's called natural language prompt chatting with generative AI. And you can do those using foundational models and LLMs. I'm sure you've heard a lot about that. The thing about it is it's very expensive, especially at scale. I'm doing a panel later on tomorrow, if you're interested. And there's going to be someone from Google, and there's actually a great blog about what it would cost Google to introduce LLMs into their search. And basically, the stock would tank. It's just that operationally expensive to do so. And the reason is not just for training of that data, and not just for encoding that data, but it's the inference cost. Every single time that you actually process that data, there's a cost associated to that GPU, right? And if you think about it, a lot of times it's very wasteful because the questions might be repetitive. So if I ask you this question, and then I ask you this question, and I ask you this question, you pay 3 times. LLMs don't have any kind of memory. So they need a vector database or something to actually store that data and be able to know if they answer that question so they don't have to reprocess. I also might ask you irrelevant questions. So if you're like a wealth or asset management company, and I ask you about aliens, you're going to go ahead and process that, not give a good answer, and it's a waste of everybody's time and money. So we want to avoid that as well. And then there's accuracy. Again, if you're an asset management company, and there's a public data set that the LLM is trained on, let's say OpenAI, it's still not enough in terms of credibility to help you service your customers. Because you, and only you, have that institutional knowledge that you've built for 50, 60 years, and you and only you have the information about your particular customers, right? What's their risk profile, what's their portfolio, what their goals are. And you don't want to share that particularly. You can fine-tune one of these LLMs, but now it introduces a bit of a security risk, a little data leakage potentially. And it's also very expensive. We talked about the training costs and inferences that it would cost on the GPU in order to fine-tune every single time. It also won't keep up, because if you're constantly changing your data, then you have to constantly fine-tune that LLM model, and that's expensive, and that takes time. And it also won't perform well. For example, if you build your own LLM, and you want to build an ensemble where you have your own proprietary, every one of those responses is going to be 2-3 seconds. If you ever interacted with ChatGPT, it takes quite a while. So you're not going to build that great user experience. And you might even get hallucinations. So the more, if you ever ask ChatGPT the same question 7 times, you might find that by the 7th time, it actually answers you in a different way. And it starts to kind of make up answers, right? So you want to keep that accuracy, that context. So what can we do about that, and where do vector databases fit in? So this is another kind of big hype term you may have heard, RAG, or Retrieval Augmented Generation. It's really about retrieving that context and providing that context in order to augment the final response that you're going to get back from the LLM, okay? And we talked about some of the ways that Redis can support that in terms of vector search. So I'll walk you through this kind of flow, right? This actually a little bit more complex in real life. But a person comes in, and let's say it's a chat, and they just put in a prompt. They ask a question. We're going to go ahead and encode that prompt so it becomes a vector embedding. And the first thing we want to do is answer, did we answer this already? We don't want to make the call to the LLM right away. We want to say, did we answer this already, right? For example, I'm from New York, and if I went in a taxi, and there was a taxi service, and I said, take me to the city, then that person has heard that a lot of times. He knows the answer to that, right? Where's the city? He knows the answer. So within a 97% likelihood, that's how we can make the kind of search criteria. Tell me if I have already answered this question. Now, what if I asked, take me to Manhattan, for those of you that know New York? Is that a different answer than take me to the city? Well, if you're a New Yorker, you know the answer is exactly the same. But a regular database wouldn't. That's why a semantic search can understand the semantics of that question. It knows that city is actually the same thing as Manhattan within the context of New York City. So let's say we have a cache hit. We can avoid the cost of inferencing on the LLM. We saved money, and we responded in sub-milliseconds. That's fantastic. But let's say we did a cache miss. The next thing is we want to make sure we answer relevant questions. We don't want to do a call to the LLM about aliens. If somebody says, do aliens exist? I don't know. I'm a taxi service. See you later, right? So we want to go ahead and create some guardrails. There's different ways to do that, but one of the ways to do it is through semantic search as well. But let's say the person is asking a relevant question. Well, now we can go to the vector database and say, what are the 3 top or 4 top answers that we have within a certain likelihood, right? So we can use cosine similarity or whatever the algorithm underneath the hood is and retrieve those answers, and also the documents or the embeddings, parts of the documents, that actually contain those answers. And we can then enrich that with any kind of chat history that might have within the session. So if I already asked 3 questions, I can add that as context, and then provide all of that to the LLM with the prompt. So now it'll come with your question, but also all that kind of like footnote or contextual history, and then you can provide that to the LLM. So what just happened? We added potentially proprietary information that didn't need to be fine-tuned within the LLM. So we're going to get a much more accurate response. We made sure that none of the noise came through, so we reduced down the costs. And we also improved the performance, right? We were able to achieve our goal in a very efficient way. So if that makes sense, and you're thinking about like how that applies to your business, the next level will be, okay, well, which vector database is the right one for me? So it seems like every month, there's a new vector database that comes along. This is, again, we're in the middle of a hype cycle. There's going to be a lot of winners. There's going to be a lot of losers. There's going to be some winners. And ultimately, there's going to be a market established, we assume. So what you're seeing right now is a lot of pure players coming up, and you're seeing a lot of companies like ours integrate or create these features around vector search or semantic search. Again, that convergence is happening, but this time in real time. It didn't take 10 years. It's happening within months. It's pretty amazing. But now, I work with a lot of enterprises. And enterprises, they have to make these hard decisions. You could play around with something if you're a small company. But if you're an enterprise, you have to think about the feasibility cost of bringing in new technology. So what does it take to have does your platform have some kind of disaster recovery capability or active business continuity? Does it operate on Kubernetes, on OpenShift in the same way that it could operate on the cloud? Does it have a managed service if I want to move to that? Does that managed service, can it be controlled through Terraform or whatever my infrastructure as code might be? Does it have integrations across the ecosystem so I don't have to build all that myself? And then, of course, does it have the basic technology or capability so it's fit for purpose for what I need it to do? So these are all the things that enterprises think about it from a technology point of view before they actually go ahead and make that decision. And of course, using a converged database like Redis, which has a decade worth of maturity already built into it and is already used by mission critical Fortune 100 type industries with security and compliance and everything built in, of course, that's a leg up. And then once we get past this technology, we get into the people, which is the real kind of crux of it. So if you're a 10,000 person organization, if you're an enterprise, think about what that means to bring in new technology, right? You have to have developer awareness and skills. What is the cost of training people? What is the cost of onboarding? How hard is it to use? What's the relevant skills in the market? Can I actually hire people to do all this? What does it take for those of you that have been through this process to move through a 3-month vendor management process, right? That's pretty painful. Security, compliance, business continuity, everything I mentioned. And at the same time, there's a macroeconomic environment that we're in. And all of these companies are looking to rationalize. They're looking to reduce down the amount of vendors that they have. And this is really playing towards the converged data platform market, where we just want to have best in breed. We just want to kind of focus in on a few of these vendors. And we really want to reduce down cost at a time where money's not cheap anymore. And we want to make sure it aligns to our architectural roadmap. So today we're on-prem, we're operating on Kubernetes. Tomorrow we might be in the cloud, we might be hybrid. We don't know exactly where we want to go, so we want to make sure this platform is fit for our architectural roadmap as well. So think about that. If vector databases make sense, you're seeing all this convergence in the market. If this is new to you, I think a lot of these headlines over the next 3-6 months, you're going to be seeing more and more of this convergence happening. You're going to be like, oh, that's what that guy was talking about. And you're going to see a lot of it specifically around AI because there's so much hype going on. So when you think about vector databases, think about everything that it takes to bring it in. And if you want to learn more, because I talk fast, I'm from New York, and I know I'm holding you back from your lunch, there's going to be a couple more sessions by a few great speakers here. So hopefully you guys can check them out. Otherwise, you can find me on LinkedIn and or somewhere here in the conference, and I'd love to talk to you. Thank you.
production data. The challenge in a lot of companies is that this requires standing up a completely separate environment. It involves creating a copy of your production data. That can take hours, weeks, days, depending on what kind of backlog your data team has in terms of access. And then that environment becomes a new environment that the data team then has to manage, a new asset that they have to manage over time. And that can create a lot of complexity, especially when you think about data science environments, prod, dev and test. All of those environments are data assets. So Git for Data is the idea of using this, the software development best practices from GitHub to manage your data. And so it uses a concept called branching, which is using a set of metadata pointers to create a no-copy clone of your production data. In this scenario right here, you'll have your main branch where all of your data consumers are hitting. We spin up 2 branches. One is for data science down on the bottom. And data scientists can play with that branch, break it, do whatever they want, and nobody's going to see the results of that in terms of your production users. On the top, we have an ETL branch. And so with an ETL branch, we can ingest new data. We can do data quality checks. We can make sure that we're happy with the data product that we've created before exposing that to our end users via a merge. And so this is a way to give everybody production quality data in just a matter of seconds without having to stand up multiple different environments for different use cases. A couple of advantages. One is isolation. Again, all of this in a branch happens without impacting other users. Those changes don't appear or aren't exposed until you merge to the main branch. You can do data quality checks. You can do whatever you want. Version control. This makes it very easy to ensure that everybody in your organization has access to a single, consistent, and accurate view of production data at all times. And then from a governance perspective, as you'll see in the demo, everything is tracked. All of the changes are tracked via a commit audit that shows everything that's happened on a branch. And of course, we have access controls to make sure only the right people are accessing the data that is the most sensitive. Cool. So that was very quick. We're going to hop into a demonstration. Obviously, I don't have a keyboard in front of me. This was pre-recorded. I'm going to talk through it. It's going to be a lot of fun. It's on YouTube. It's great. There we go. All right. So this is Dremio Cloud. And as I mentioned, we have 2 different products here. We have Dremio Sonar, which is our query engine and semantic layer. We have Arctic, which is our Iceberg catalog with Git for Data capabilities. You can do a lot of this work in either. I'm going to be running some queries, so I want to jump into Sonar first. So I'll get into my project. I bought an SUV recently, had a baby, so I've got cars on my mind. So I'm going to pretend that I'm a Ford dealership in Annapolis. I have a catalog. I have an Iceberg table. This table is July sales of trucks and SUVs. So I'm going to jump in here and show you the table. And I am going to show you the table. There we go. All right, so this is the main branch. We don't have any other branches yet, and you can see that this table has all of the different makes and models. It has the MSRP, and then it has the actual units sold in July. Now, say I hear from corporate that they're going to bring back the Ford Excursion, which is their heavy-duty SUV. I want to run some scenario analyses. I want to see what July might look like if I had an Excursion to sell. The first thing that I'd have to do is I'd have to request that the data team stand me up a copy of the data. I'd have to have a separate environment because who knows who's using this July sales data in their dashboards. That's the old way. With this new way, all it takes is a create branch function, which again will happen in just a second. It gets better, I promise. There we go, we're moving. All right, so I'm going to create this Ford test branch. And just sort of like a magic trick, I'm going to hit run, and this is going to be my new branch. Cool. So now we have production quality data in an environment where we can't break anything. We're going to jump over. As you can see, the commit history is the same. Nothing's happened on this branch yet. I'm going to switch over to this branch and switch the context to the branch so I don't have to continue to reference it as I do things. And so now I'm in an environment where I can't break anything. So let's play around with the data. I'm going to first add a line for the Ford Excursion. And I'm going to assume that in the first year, in the first month that it's available, I sold 4. Uh-oh. Can you guys see it? Oh. I didn't prepare a dance or anything. The computer died? Imagine, if you will. Yes. Yep. Yeah.
And then at a later time, you actually check it into Git or like your own company's cloud visual or something. Is that the idea?
So it's accessible, it's tracked, it's audited, all of that. The branch isn't meant to persist forever. Eventually, you'll probably want to toss the branch and create a new branch because your production data will change over time. We can do things like tagging a view so that, and I would show that if I was showing the demo right now, you can actually, once you create a view, tag it, and that persists even after the branch is thrown away. So branches aren't meant to persist forever, except for the main branch.
But the data itself, let's say I had the data in a variable fashion in some database.
Yeah, yeah.
Now we have commissioned it so that we have a separate copy of it, or
No, it's 0 copy. Yeah, it's not actually a copy. It's like it's a snapshot metadata pointers that create sort of a clone. Yeah, data stays wherever it lived. Yeah.
but if I make changes, then
You can't go back? Oh, you're back. Okay. Yeah.
so if I do make changes to the data, then those changes are still residing just as part of my the Git changes, but not persisted into the actual.
Right. Correct. Until I make a merge, and then it will update the main branch. Okay, are we good? We're good? Okay, start rolling. Okay, so I've added the where am I? Excursion, that's right. Okay, and now, because I am gonna assume that I didn't just sell 4 net new excursions, maybe I upsold an expedition user or 2, I'm gonna change the number of expeditions that I sold. So that'll take just a second. And so I've made a couple of changes to this data. And now I'm going to run a select star so that we can see those changes in the table. Cool. And there we go. Changes are there. You can see I have a line for the excursion. I have an updated expedition number. And again, this is in the Ford test branch. The main branch remains unchanged, so my production users are not going to see this, and now I'm going to run a select on that as well so that we can see that the data has not changed. Cool. Yep, and so there it is, and the nice little lag showed you that the data, in fact, has not changed. So let's tag this view so it's easily discoverable by a lot of different people. I could do that in here, but I would rather jump over into Arctic and show a couple of the features of the catalog prior to jumping back here. So I'm clicking through Jello. Okay, Arctic, there we go. There's our catalog. All right, and so we have data, we have our commit history, we have our tags, and then we have our branches. So data is literally the data. That's all of the data that is in this catalog. And here I'm showing our privilege control, as well as our table optimization features. So obviously you have access to who controls or who accesses your tables. On the table optimization, that's an Iceberg function called compaction. Rewrites small files into a larger file, which solves a small file problem if you're doing things like micro batching or streaming workloads so that your data stays performant over time. And then I'm going to hop over and show the commit history. And so this is a full audit of all of the changes that have been made on a branch. We obviously have both of the branches. You can see all of the changes, who made them, what they were, and when they were made. Tags are going to get more interesting over time after we add one. We're going to go to branches now. And so these are all the branches that we have right now. The commit ID, what happened, and then who made the change. We'll hop over to our test branch and show that you can actually do a lot of what I've already done in a low-code, no-code way. So we have the data tab, which will take you back to data. If you don't want to use SQL to merge, you can merge it here. You can create a new branch. And then over here we have tags, and then we have drop branch as well. So let's add a tag that's a little more descriptive than 20 alphanumeric characters so that people can find our view. And we'll do July sales with excursion. July sales with excursion. Cool. And we have now added a tag that is in our tags tab, as well as in our commit history and branch view once we get back over to the SQL runner, so that it is very easy to find and show that view. Yep, so I'm gonna open up the branch view. You can see under other branches, we also have our tags, and I can reference that, make that the context if I want, and then I can show that it is in fact the view that we want it to be. Cool. So that is the view. Now, obviously, this is a test branch. We don't necessarily want to expose this stuff to our end users, but I just want to show how easy it would be if we did use it for ETL or data quality to both make changes to the main branch and then revert those changes if we didn't, in fact, want to make them. So it's as easy as a merge to main command. And so now all of our production users will be exposed to what we were doing in that branch. All changes are made atomically, so all of the commits or none of the commits. And then, yep, I'm going to show the main branch data has changed. This is a bit like a magic trick. Cool. Now, let's say I didn't want to make a change. Let's say somebody called me and said, "You're a jerk, you broke my dashboard. I need things to go back the way it is." You can roll back your entire catalog with a single command by identifying the branch header or changing the branch header to the commit prior to the change that you didn't want to make. So that's the command. We're going to hop in here. And we're going to copy the commit ID. don't apply, although you can use the apply function. Very helpful if you actually want to go back and make sure that's the view that you in fact want to make the branch header. So you can take a look at that. And there we go. We've rolled back the changes. It is like nothing ever happened, and all our production users are happy again. And you never believe that the woman who got sawed in half is fine until you see it. So we're going to run one more select statement. And there we go. No changes have been made. We've rolled back the problem changes that we made when we merged. So that's the demo. It's pretty easy. In about 10 minutes, I've shown you that you can create a zero-copy clone of your data in just a couple of seconds. We made some changes. We committed those changes, and then we reverted those changes to avert disaster. So pretty easy, intuitive tool. Lots of fun, lots of possibilities in terms of standing up your production data so that other people can access it safely. Again, my name is Jeremiah Morrow. I'm with Dremio. If you want to talk more about data as code or our SQL platform, please stop by our booth. I will also be hanging out here afterwards to answer any questions. Enjoy the rest of your conference.
We're good to go? Sounds like it. Hi. Feel like I'm doing a stand-up comedy. I don't have any jokes for you. My talk today is about large language models, vector embeddings, and vector databases, how they put them all together. Right, by the way, my name is Anton Umnikov. I'm a principal solution architect in Redis. Right, we have a fancy title that includes Hello World. And for me, Hello World today is the foundational paper that started the generative AI revolution as we know it today. Right? Hello World of Transformers. I usually, every conference I go to, I count the number of times this paper being mentioned in all the sessions. Right? I'm surprised I haven't seen mention of this paper in any of the keynotes today. But attention is all you need. Foundational paper published in late 2017 that talks about transformer architecture. That essentially introduced the architecture of transformers. Quick show of hands, who've seen at least the name of that paper, maybe one of the pictures on the screen? Yeah, like pretty much everything. Now, show of hands who actually read the paper. Okay, few people actually read the paper. For those who didn't, paper introduced architecture of transformers, actually two of them, encoder transformer and decoder transformer. Right? And author of the paper used both of these transformers together to solve the task of machine translation, translation from one language to another. They started with English to German translation, then they did the same exercise for English to French. They set the record in terms of accuracy on what is called a BLEU score. And BLEU score is used to evaluate the quality of machine translation or even human translation, where 0 being total garbage, right? And 100 is a perfect translation, frankly unattainable even for the best human interpreters, human translators, right? More importantly, the transformer architecture not only set the record in terms of quality of translation, it happened to be very powerful, very economical architecture to implement and train. This architecture is very parallelizable, so it's easy and fast to train these transformers in order to achieve the task that you need. Again, if you look a little bit deeper, there are two types of transformers: encoder transformer on your left that essentially extracts the semantic meaning of that text, and turns it into vectors. Right? Then these vectors are being fed into the decoder transformer, right? That one by one translate the semantic meaning into the output text, right? So, but interesting thing happened right after the paper was published, right? That's late 2017. People started to use these transformers independently. Right, so encoder transformer, right? And encoder transformer has been trained to understand the entire semantic meaning of the body of text that you translate in. So essentially the way it's trained is they mask random word within the sentence or paragraph, right? And let machine predict that word. So it has attention both left and right to the text, right? And right away, this architecture was picked up by a lot of researchers, and the architecture called BERT emerged, which happened to be like best thing since sliced bread in machine learning, in natural language processing in 2018 up to middle 2021. Right? The decoder architecture, right? Decoder architecture predicts the last word, the next word in the sequence. So attention here is only to the left, right? And it does predict one word at a time, and then the whole thing is being fed back to the transformer to predict the next one, right? In the original paper, it takes the vector embedding that embeds semantic meaning of the text, and then you add word by word and you generate the translation. Then someone really smart thought, do we really need this vector embedding in front? Can we just feed this thing beginning of our translation or whatever it is and let it complete it? And guess what happened? This is beginning of GPT architecture. So ChatGPT as we know it, Llama 2 as we know it, is essentially decoder transformer from our original paper on steroids that does one-by-one completion of the beginning text. Right? If you ever chatted with ChatGPT, you see how it like does it word by word. Right? It's not done for the dramatic effect. It's done just because it's literally word by word, token by token, generate the completion of the text that you fed it. Right? So these transformers, decoder and encoder, started to live their own independent life. Right? If we look at the evolutionary tree of large language models, you would see that up to 2021, most of the effort was on the BERT and their derivatives that are doing extracted semantic meaning from the text. It's great for things like sentiment analysis, for comparing semantic similarity. This is the time that we in Redis saw the future in this technology, and we implemented vector similarity search, basically comparing these embedding vectors at scale and identifying most similar vectors. And then in last year, ChatGPT happened. Everybody all of a sudden understood that, hey, this technology, this decoder-only completion engine, has the power to change the world, right? And here we see all the like encoder-only model, BERT, and all the derivatives, and the decoder-only is all the generative AI as we know it, right? So we're going to talk about vectors and vector embeddings. Like essentially, the engine generating the vector embedding is kind of a smaller, lightweight cousin of the generative AI models that we use today, right? Encoder has just hundreds of millions of parameters. It's relatively small, like size of encoder is maybe hundreds of megabytes, maybe single digits gigabytes, where decoder architecture like ChatGPT, they are huge. Like they require specialized hardware and so on and so forth. So really big difference, but they come from the same root, from the same original paper. Attention is all you need. Now, what brings them together today? Again, you probably heard retrieval augmented generation, grounded LLM, avoiding hallucinations many times today, and you'll be hearing about that over and over again because that's the hottest topic in today natural language processing. Like to position retrieval augmented generation, it's kind of in between your traditional search. Think of Google or Bing or your SharePoint, and the pure memory-based things like ChatGPT, Google Palm, Facebook Llama, and so on. Right? It's useful to do whole bunch of things. Like probably the biggest absolute necessity for retrieval augmented generation is like there's just so much you can feed into the prompt window, token window of large language models, so you can't feed all your internal data into ChatGPT and say, hey, answer me the question. You need to pre-select the data that's relevant to your question, right? Avoiding hallucinations, giving you observability and traceability of what happened with your system, like a whole bunch of positive sites. Again, there are a lot of talks about retrieval augmented generation. But if you think about like high-level architecture of retrieval augmented generation, retrieval augmented LLM, you need three components. You need embedding generation, like think of BERT and derivatives. You need vector database, and you need large language model. Right? If you'll put it all together and really deploy that to production, that's one of the examples of how you would do that. You take all your documents, you put them in a blob storage, you split it into chunk, load into vector database in the form of embeddings, and then your user asks the question, right? You run it through the same embedding engine, you find the most similar chunk of text from your internal body of text, and you feed it into the large language model. In this case, we're talking about Azure OpenAI. Right, we at Redis obviously use Redis as vector database, but you're not limited by Redis only. And this is the, so to speak, POC in the box that you can run. Just drop your files, PDF documents in the folder, run Terraform apply. You would have entire infrastructure totally private to your organization. Right? If you do the same thing on Google Cloud, right, you would use Vertex AI Palm model as your large language model. You might use Gecko engine from Google to build your embeddings, or you might use something like embeddings from Hugging Face. Right? There is no dependency between embeddings and large language model. Right? If you'll put that all together, again, you have three components here: embeddings, vector database, and large language model. We're not focusing on large language model, we're focusing on the two other things today. Right? Embeddings. You can choose embeddings that are out there. Hugging Face is a great source of embeddings you can run on your own hardware, on your own notebook, but you can use embeddings from the vendor of large language models, such as Ada from ChatGPT or Gecko from Google. In terms of what you use for your vector database solution, again, there are multiple choices there. There are libraries. FAIS is a great example. F here stands for Facebook, another great contribution of Facebook or Meta into natural language processing world, right? But it's a library. It's not really a database that you would put a production load on. There are purpose-built vector databases such as Pinecone, and there are traditional database vendors such as Redis that put vector database similarity into the existing database. Right? So let's talk about how do you choose the components. There was a great talk earlier today, right, explaining what vectors is. I'm using the same example. Right? Vector is like multi-dimensional set of numbers. If you take vector for representing king, subtract vector of the man, add vector for a woman, you most likely get the vector for a queen. Right? I would not go into details of that, but like pretty much all the vector embeddings model allow you to digitize semantic meaning of the text into set of numbers, right? And that's what embeddings do. And there are a whole bunch of other things that you can do with vector embeddings and vector databases, not necessarily requiring generative large language model. For instance, one of the early adopters of Redis vector similarity search, company from Australia, Relevance AI, they used embeddings and Redis as a vector database to identify cheaters in online multiplayer game. I have no idea how exactly, but somehow they turn into vector the gameplay of particular player, right? And they looking for outliers. So whatever they do, they solve the problem of identifying cheaters in multiplayer game using vector engine. Right? But there are other applications for vector databases totally outside of generative AI as we know it today. So, how do you choose embeddings and vector database? Again, embedding doesn't have to be from the same vendor as the vendor of your large language model. If you use an OpenAI as your large language model, you don't have to use Ada as your embeddings. Actually, if you look at the Hugging Face is a great source of embeddings that you can run on your laptop or on your cloud instance or in your notebook. Right? They maintain the benchmark of those embeddings. Right? And OpenAI Ada is just number 10, it's not number 1. It's aware of a lot of languages. Embeddings are really high quality, but based on this benchmark, it's not necessarily the best embedding out there. So look at the cost, look at the performance, right? If you use an OpenAI embedding, the only way you can use it is to send requests somewhere out there to the OpenAI servers and retrieve that. Why don't you use that right within your own runtime? Right? Cost is actually the very big factor there. Right? If you look at the OpenAI price list, right, you would see that cost of embedding per token is 20 times less than cost of generating the data using large language model. Now, you might think, oh yeah, that's peanuts, I would not worry about it. You should. Because if you essentially looking for a needle in a haystack, you need to build embeddings for entire haystack, and in your development cycle, you'll be doing it over and over and over again because like, okay, what is the chunk size, like how they overlap and so on. Right, so my personal experience working on one of the projects that been on the previous slides, 70% of my OpenAI build was for embeddings, not for large language model, not for generation. Right? And embeddings, unlike generative large language model, are really easy, really lightweight, so you can use them in your own solution. If you're using high-level frameworks such as LangChain, like it's 2 lines of code to enable OpenAI embedding, 2 lines of code to enable Hugging Face embedding. Right, so seriously consider bring your own embeddings if you're building retrieval augmented generation project. Right, vector database. Right? On the right, you see the math behind the vector similarity. Cosine similarity, my kids are in a high school, they can probably figure it out on their own. Right? It's simple, it's hard to do wrong. If you're doing that in scale, you need to build secondary indices, but again, the algorithms for that are well known, well publicized. If you have 2 vector databases that give you substantially different results for the same queries on the same algorithm, one of them, at least one of them, should not be in software business. Okay? Right. So, if you think about vector database, think about vector and database. Vector is math. It's simple, it's well known, like everybody should be able to do that. Database part, scalability, high availability, especially security, if we're talking about enterprise cloud, this is the hard part. Right? We have a lot of customers, traditional enterprise customers that use in Redis, like for their cache and session store needs. They talking to us not necessarily because they see Redis as the best vector database ever. They see us because we are vendor that pass all the security clearance, has all the certification they need, and that's already approval vendor, right? For like big bank, it might take up to a year to get master service agreement, vendor agreement, all the security clearance, and so on. Right? So think of the database part of the vector database, right? And here, this is just a list of all the security credentials and certificates that Redis has as a database. But again, if you choose between pure play vector databases that have to catch up on the database part, especially this enterprise part, such as security, scalability, and compliance, right, and traditional databases that aid in vector similarity, my bet, regardless of the fact that I work for Redis, would be on traditional database vendors, at least at this moment of time. Right. So how else can you use database such as Redis in large language models, right? First one is a context retrieval, is vector database in the retrieval augmented generation model, right? Another one is LLM cache. My colleague Tyler Hutcherson would be doing tomorrow talk about using Redis as a semantic cache for large language model, right? So that's traditional business for Redis, what we've been doing for a lot of years. Now we're adding the semantic layer to this cache. And LLM memory. If you ever talk to ChatGPT, to OpenAI, like it kind of remembers the context of all your previous conversations and context of your conversation. The ChatGPT itself, the model, does not. Like it's a database that sits on the side that remembers it. And actually, ChatGPT already using Redis just for that. It's kind of weird to bring the outage as a bragging point for the database vendor, but what actually happened, in March 2023, ChatGPT had a worldwide outage. And the nature of the outage was like customer would start seeing under some weird circumstances conversations by other customers, right? We are a vendor of Redis. They contacted us, quickly identified that it's a problem in the client-side code connecting to Redis. Right, but we know that, we help them to fix that, we get the best endorsement the database vendor can get from a company like OpenAI, right? They would continue to use Redis for that purpose and hopefully for many other use cases. So, if I can quickly summarize like what we talked about today. So, vector embedding, like something that generates embedding, and the generative AI as we know it today, they came from the same paper. Attention is all you need. You can think of embeddings as a smaller, younger cousin of generative LLM, right? If you build in retrieval augmented generation or retrieval augmented LLM. The term you might hear is grounded LLM, grounded generation. You need embeddings, vector database, and large language model. You can choose 3 of them independently. You don't have to rely on embeddings from the LLM provider, right? And pick your embeddings wisely. Embeddings is something that you can totally run on your own. I would think twice before provisioning infrastructure for running something like Llama 2, but for embeddings, it's no-brainer. You can do that, and you would save a lot of money if you do that, especially in the development cycle, right? And then you choose in a vector database. Vectors are easy, databases are hard, so look closely at the database part of the vector database. That's it. I don't know if we have any time for questions. There are a couple of links for you. Redis Ventures GitHub is a great collection of resources that you can use, like all the solutions that I showed you with Azure, with Google AI are on that GitHub. You can run Redis stack locally, even right within your own notebook, or you can provision free version of Redis in the cloud with vector similarity search, and so on. And on that, thank you very much. And if we have any time for questions, I don't think we do, but I'm here in our booth right in front of the registration desk, so we'll all will be there. And happy to talk to you.
Sorry. Okay. Yeah. Yeah. 3. Is it on? Can you hear me? Okay. All right. Okay. Good afternoon, everyone. And thank you, Data Science Connect, Amelia, and Neo4j for the opportunity to speak here. So today I'm going to talk about contextual and semantic information retrieval. I'm Fani Datar. I'm a Director of Graph Data Science at Neo4j. And specifically, I'm going to talk to you today about using knowledge graph to ground LLM responses. What does it mean? And I hope I'll convince you by end of this talk in like next 15 minutes that knowledge graphs are the amazing data structures that you would be looking at when thinking about large language models. LLMs are amazing, right? In my role 2 months ago, every other conversation included generative AI, and nowadays every conversation is about generative AI. So, and superior natural language understanding of LLMs, you've been hearing about this since today morning, even before coming here. All the great things that you can do, but still there are these challenges. There are these things that are barriers for adoption, personally as well as enterprise-wide adoption. And there are many things that are familiar to, I believe, most of you, almost all of you. But I'm going to point out 2 specific topics: reasonable answers, but not always accurate, and lack of enterprise domain knowledge, right? So those are the 2 topics I want to focus on, and because LLMs are inherently probabilistic models. They are really good at giving you reasonable answers, but the answers are not always factual because they don't know. They are only exposed to the data that they are familiar with, and they are not exposed to your domain or your organizational specific data. So how do we deal with that? And we still, all of us agree that this is a great opportunity. We all want to use it. We all definitely want to use it, but then because of these barriers for adoption, it is not there yet. I mean, there are no applications in production yet. It is still in the phase of lots of POCs going on, lots of different tests, different initiatives, but nothing concrete yet. So it is becoming increasingly common. If you look at various blog posts, various discussions that you're part of, it is becoming increasingly common that you need an additional data store. LLMs alone cannot give you a solution. You need an additional data store for grounding the responses or providing your factual information. Because if you look at enterprise data has both unstructured and structured data, right? Unstructured data is where we had lots of problems with, and we go to great lengths to capture data, break it down, extract facts from unstructured data, store it in a structured format, again, running analytics and so on and so forth. And in unstructured data, we have been struggling with different NLP pipelines until like December, and suddenly, it has become really easy to embed not only the sentences but paragraphs to documents into vectors, and then finding similar meaning text has become pretty easy or pretty powerful, right? But structured data still remains. And structured data, 98% of all the structured data are facts, and 2% are around dimensions. But those facts are really important for all the enterprises and businesses, and we rely on that data. So how do we take advantage of LLMs as well as not to lose on getting the real data from your enterprise databases? So here comes knowledge graphs. And if you look at other types of data structures like SQL and NoSQL and knowledge graphs and graph data structures, all of them are really great in providing the context that are required to ground large language models. However, if you really want to go beyond a simple understanding of what that particular entity means, but also how that particular entity is connected to its neighborhood, how is it related to your business overall, then you need a data structure that goes beyond storing data in rows and columns or in a form of a document. You need something like a graph data structure that can span across different data silos, that gives a unified picture of your data, and that you can cross from one part of the data structure to the other part of the data structure pretty easily and retrieve those patterns. And that's where graph databases come into picture. And knowledge graphs are a type of graph that has additional information in it. So graph data structures connect data from different silos, and the relationships between different entities and different silos become explicit in a graph. And in a knowledge graph, besides that factual data, you have taxonomies and ontologies that relate to the domain-specific knowledge and the semantics between different entities that describe your business. And once you have that rich connected data, then you have the necessary context that makes the whole response from an LLM more contextual to your business. And on top of that, knowledge graphs also allow you to enrich the context by adding more information. How do you add more information? Sometimes the relationships in your data is much more important than the data itself. And when you can derive insights from those relationships, then knowledge graphs can be used to capture that additional context as well. The more you make data contextual to your business, the more relevant these answers will be for your whatever downstream applications are. So today, we are going to go through these three phases: connect, enrich, and consume. And the third part of consumption is where LLMs come into picture. We still want to take advantage of the superior natural language understanding capabilities of large language models, superior text summarization capabilities of large language models, but we don't want to compromise on the data that's relevant to our businesses. That's why we need a combination of these two powerful technologies. So for those who are not familiar with knowledge graphs or graphs in general, what can you do with a knowledge graph? I'll take an example. Remember collaborative filtering and generating recommendations by looking at preferences? Let's say there is this customer, Jane, and you want to find recommendations for Jane. If you are using some kind of matrix factorization methods, you look at all the users of your business, their purchases, their preferences, and then boil down to a user matrix, a low-rank matrix for a user, trying to find similar users for Jane, and then trying to find recommendations for Jane. So now the curse of dimensionality comes into picture, the recommendations are still not personalized, and so on and so forth. On a knowledge graph, it becomes a simple graph pattern match. You start from the customer, you start from Jane, and then probe the local neighborhood find similar users to Jane, and then start recommending products to Jane. So the whole thinking about how do you personalize, or how do you do recommendations, how do you generate insights, it changes on a knowledge graph. And sometimes it is as simple as traversing 4 relationships. Like my colleague was saying today, you have trillion relationship graph, but you don't need to cross more than 1 relationship. That was amazing, right? So you have terabyte of data. Yes, but for insight for Jane, like I said, you probably don't need to go beyond 1 hop from Jane and then go find similar users and start finding the products. So knowledge graph is an amazing data structure that makes these relationships explicit, and then you can generate those insights pretty easily. Now the part where I talked about enriching the knowledge graph is, okay, now knowledge graph captures the data, the factual data, and the relationships between data. And we can also enrich the graph by adding more relationships. And what are these more relationships? Those are the derived relationships from the natural relationships, like if you say, hey, there are 2 people who have made similar purchases in subsequent store visits, then there is some commonality between 2 people. By running a pattern match on a graph, you can create a new derived relationship, and then when you want to consume and ask the question, I want to find a customer that is similar to this customer, then all you need to do is go traverse this derived relationship and then grab the other one. So this additional context that you generate is what we call enrichment, and this enrichment can be done in multiple ways. One, by running graph queries, which are simple pattern matches, or you can go a little bit advanced and run graph algorithms like community detection or clustering or anything that has to do with relationships and algorithms that work on relationships. Or you can reduce the dimensionality, generate an embedding representation of nodes in the graph, and then run unsupervised approaches like clustering or some other downstream insights, like a previous speaker has shown a list of things that you can do with embeddings. And so for some more examples of insights from graph algorithms, again, these insights are coming from the graph algorithms, and then you can add them back to the graph, which will enable better context, more information from your data. For example, if I want to do what-if analysis on the graph, then I can run algorithms on a graph and then change the scores of a certain nodes in a graph. And then when I start asking questions about which data center is prone to cybercrime activity, then I can just go and probe the graph, pick up the nodes with a higher centrality score, and then use that as a response to the user. Because if I'm a cybersecurity analyst looking at my knowledge graph, I will not be interested in some generic information from an LLM, but I would be interested in getting the information from the graph, not only based on the factual data, but from the derived data. So you see the insights from these graph algorithms enhance the context, enrich the context in the knowledge graph, and this knowledge graph as a data structure captures that additional knowledge as well. So by using the graph, again, by using the graph, you're making use of the relationships. You're taking advantage of the relationships. By enriching the graph, you're taking advantage of the insights that come from your data. And all of this, we are building towards consumption at a later point. And we can also use LLMs for enrichment, like the previous speaker was also showing, and some of the speakers were showing. You can take the embeddings. They can either come from LLMs or bring your own embeddings from some Hugging Face models. And you can bring them to the graph and then store them as node properties. And this is one of a common use case where you have a bunch of text lying around, like PDFs. You take those PDFs, create chunks of text, and those chunks of text are converted into vectors, and those vectors are stored as, those chunks are stored as nodes in a graph, and the vectors that correspond to those chunks of text are also stored as node properties. Now you can take this graph and then use a native vector indexing in databases like Neo4j, and then you can run semantic search on your graph. So the semantic search is running on the graph, provides the local information that's domain specific, organization specific, and then you can use in summarizing your answers. And one more thing is you can even generate a richer representation. So in this representation, these embeddings capture the semantic meaning of chunks of text. In this representation, which are node embeddings are vector representations of nodes in a graph that capture the topology around that node, the structure around that node. Node embeddings or graph embeddings capture the topology, and when you combine the node properties, which are the semantic information, then these graph embeddings are even richer. They combine both contextual and semantic information in a single vector. Now if you do matching on those vectors, now if you index those vectors and start searching for similar vectors, the information that you get out of a knowledge graph is going to be contextual as well as semantic. And when you finally look at the results and then look at the, and then also take advantage of the graph traversals, then you get much more relevant, accurate, and contextual answers when you combine a knowledge graph with your LLM. So now, step number 1 is a knowledge graph where you build the graph with relationships. 2, you can enrich the graph in these few different ways. And then once you have that, then comes this consumption patterns. Now, this is where my topic for today is semantic and contextual information retrieval. Information retrieval from the knowledge graph, which includes both semantics as well as the context. And here is a simple pattern that shows how do you retrieve knowledge from Neo4j. Neo4j is a graph database, and today I'm specifically talking about knowledge graphs that are built using label property graph technology in a database, Neo4j, right? So the flexibility of storing data in form of nodes and relationships, as well as properties on nodes, properties on relationships, different types of properties on nodes and relationships are available in Neo4j, and the knowledge graph that I'm talking about is built on Neo4j. So it's in this simple picture, you see that there is an application, user-facing application. User asks a question that is sent to an embedding model. It could be LLM. Generates. I mean, the embedding comes from the same. The embedding is from the same distribution as the embeddings that you generated for your text documents. And you get the implicit results, which are semantically similar based on vector matching. And then you can combine that with explicit results in relationships and derived relationships in your knowledge graph. And then you can take those results and then again combine them to put them together, ask LLM for summarizing the results, and then you can send it back to the applications. This is one pattern. And similarly, there is a different pattern where you want to take the, you're going to ask the LLM to generate cipher code so that you can run the cipher code on Neo4j database to extract results directly from Neo4j and then ask for generating an answer. So we have a framework that you can use and then integrate large language models with Neo4j database by using LangChain framework and using this graph cipher QA chain to get the context, which is the graph schema that you attach to your prompt, along with the training sample, a bunch of cipher queries, and then the question, and give it to LLM so that you can generate a cipher that corresponds to the schema that you provided as the context, so that you're not hallucinating there, or you're not creating new variables, new schema elements, and so on and so forth. And then you can also use fine-tuning, where you can have a bunch of examples, fine-tune a model, etc. But you can set up this framework pretty quickly and easily, and you can test this knowledge retrieval example with Neo4j. There are a couple blog posts that we have that we can share, which shows you this pattern of retrieval augmented generation using Neo4j knowledge graph as a source for contextual data. And this example is something that I really like. By the way, this is the retrieval augmented generation pattern with Neo4j. Here you see the Neo4j as a database, provides you the context that you need, and Neo4j, like I said, is used to build that knowledge graph that I talked about. and this knowledge graph will give you all the good things that I talked about for relevance, context, and then accurate or factual data. So, what, as an example, if you want, as an example, if you ask an LLM about this Hurricane Calvin, which passed Hawaii in July, when we were working on this, what is the impact of Hurricane Calvin? Then obviously, if you ask an LLM, you get Hurricane Calvin is caused by some flooding. It just flew south of Hawaii and so on and so forth. But if you want to refine this question and say, who's asking? Like, if an insurance company analyst is asking this question, then okay, it may be okay to give him an answer that Calvin just passed Hawaii. But what's more important is there are 50 policy holders in that region that are at the risk of that property loss, and that's what the impact of Hurricane Calvin. So how do you get that context, and how do you make a determination that this is what this particular analyst would need, right? So, like, there are these different patterns that I talked about that can be used for fine-tuning and developing relevant cipher, generating insights, etc., and then orchestrating this whole process to achieve what we are after: semantic and contextual information retrieval. So just to summarize, if you start with your data, unstructured data, then you can get the first step done pretty easily. And then there are many tools out there where you just take those unstructured data, do some experimentation. How do you chunk it, generate vectors, put them in any vector database, and then you get the similar documents and content for user queries. Awesome. That works for some applications. But then once you start combining your structured data, then you want to go beyond the first set of results and then start capturing other information. So if you look at topics like pre-filtering, post-filtering, meta-filtering, etc., that is something that's becoming increasingly common. Many tools are building, functionality around it, but graphs, knowledge graphs, already has that built in. So if you want to add context, all you simply need to do is take advantage of graph traversals, pattern matching. So after you find similar documents, you find connected things immediately within 1 or 2 or 3 hops out, and then get it to consume directly or give it to LLM for refined answers. And finally, once you start including graph algorithms and graph neural networks and all graph machine learning that's available in Neo4j, then you can further improve search relevance and insights by enriching your knowledge graph with the insights that you get from your existing data. So that's what I wanted to show you today, and I hope it has enough content to make you interested that knowledge graphs are providing you that extra information that you need compared to the other data stores. That's it. Thank you. Okay, yes. So Neo4j is a database, and vector indexing is a functionality is a feature of Neo4j. So if you are asking, do I need both vector databases and Neo4j? No, you don't need. You can take the vectors index in Neo4j. Embedding algorithms, node embedding algorithms are included in Neo4j Graph Data Science Library that you can directly run on Neo4j graphs. Thank you. Oh, yes. So, first of all, understanding the user intent is the first part. Once you understand the user intent, then the corresponding cipher query is generated by this large language model. To help large language model generate the right kind of cipher query, you give some few short examples in the context. That's how you could generate the cipher query to extract results. It is still, we are still working on it. We are still trying to understand the best way to contain the results or the cipher queries that run, but it is proving to be pretty powerful. So have we experimented embedding cipher queries itself? No, we haven't, because embedding cipher queries is not gonna give you that much advantage, I guess. But embedding graphlets and using the embedding vector, finding, like when a user asks a question, instead of finding a node that's similar to the user query, if we can find a neighborhood that's similar to the user query, then that provides you a better context for grounded response. So we are experimenting with that. Yes. Right. Yes. So so there are two parts to that question. So the question is, how do you verify the accuracy of the answer? So the first part is like when a cipher is generated and a cipher query is run on a database, whatever the result that comes out of the database is going to be factual, because the data that you put in Neo4j is the fact data. But then the question is whether the answer is complete. So the first is accurate, yes, but complete, that's where we need to figure out. Like we need to experiment with fine tuning, and then we need to experiment with the extent of coverage these cipher queries provide. So there are a few metrics that we are trying. One is comparing the responses. Like what kind of examples would train an LLM to give a better response, so that you are not missing out on some things like, for example, there is a patient journey database when we were looking at a question like, how many patients that are 30 years or older that are diagnosed with diabetes, and what happened to them 90 days after the first diagnosis. So now if you start thinking about it, the cipher query is pretty complicated, because now you need to do a couple filters and then a path matching and so on and so forth. So what kind of examples would you require so that would you need to send to the LLM as part of your prompt augmentation to get such certain questions? It's something that we're still working on. But that's actually working on with different customers and prospects, because they are schema dependent and the analytics and question dependent. Sorry. How much time do I have? I think I'm 3:15. Okay. All right. Cool. All right. Thank you. Yes. Yeah. Yes. You have a question?
So in one of the slides that you showed, you were basically combining the prompt that comes from the user and the context from the database.
Yes.
So that combination, is that just simply, I think the slide before.
Yeah.
At node 2, when it's combining prompt, context, and relevance.
Yeah.
Is it simply like adding two different vectors, one coming from the database and one coming from the prompt?
No, prompt is the English language prompt, right? So sorry, the prompt includes context and relevance, meaning the prompt is just the question that posed by the user, and then the graph schema that comes from this graph cipher QA chain, and then the examples that we added to the prompt, and then some other directions to the LLM what to generate. So the prompt is a package that goes to that point number 2. But what happens is, you see the prompt when it goes to LLM, generates cipher, and then Neo4j generates results, and the question will be combined with these result set and then sent to LLM. Okay? So there are two different paths there. One path is generating cipher, the other path is question and then the answer set and then asking for summarization. Okay, sure. Yeah, thank you.
Should we do a test? Test, test. Okay. Test, test. Good afternoon, everyone. I'm John Kang. I work for Cox Automotive, and I'm going to be spending the next 20 minutes talking about how we at Cox Automotive solved and are continuing to solve some of our capacity-related challenges using a combination of Python and Dash Enterprise. So a quick introduction to the company I work for and myself. If you're not familiar with Cox Automotive, we produce a lot of business-to-business products. You may know some of our online brands like Auto Trader, Kelley Blue Book, Dealer.com. We're owned by Cox Enterprises, approximately 50,000 employees under the Cox Enterprise brand, with about $22 billion in revenue. A sister company, Cox Automotive, is Cox Communications, the cable company. The specific business unit I support is called Manheim Auto Auctions. So about 18,000 employees, $3 billion in revenue, largest North American auto auction network in North America. And we were facing a problem with determining how much skilled labor and equipment we needed across our 50-plus US auto auction sites. And my specific task and role was in planning and analytics to help plan for skilled labor and equipment across these auto auctions. So quick executive summary. I'm not going to touch on all these points, but at a high level, we were faced with this problem. How much equipment do we need? How many people do we need across our auctions with varying demand at 50-plus sites? We needed a scalable, reliable solution that could work not just for technical users, but business users as well. This needed to be interactive. It needed to be a data application, not a dashboard. And it needed to be easy enough for non-technical business users to use. So getting into our challenge, right? We needed to support decision support for site staffing and equipment investments. So diving into the problem. So picture summer, fall 2020. We're coming out of the COVID restrictions. A couple of our key clients wanted us to quickly ramp up our capacity. And at Manheim, we had this operational capability called reconditioning. So reconditioning is where you repair, restore, and renew a vehicle. So for two sides of the business. Wholesale, we're supporting the auto auction. So a car may come from a dealer or a commercial client. It may not operate because the batteries don't work, the tires are flat. We'll perform that work so it can go through the auction. And the second side of the business, it's called the retail side of the business. We will recondition a vehicle for a dealer so that it can go to a consumer. So say you're buying a car online, possibly some of these cars may be reconditioned by us, but you may not know that. So we're facing these challenges. We had high amounts of growth, and we weren't able to fully support this growth. We were running into operational challenges. We had high overtime. We weren't meeting our customer service level agreements. So I was tasked with determining what was the optimal level of equipment and people based on our historical averages and models of demand and supply. Demand is cars we need to recondition, and supply is like how many people do we have? And we're not talking about unskilled labor, we're talking about technicians. So if you think of like, say, a mechanic shop, right? You've got technicians there. As you know right now, right? Hiring is difficult. Hiring was difficult back then as well. It took time to ramp up and as well hire people, so we needed to know beforehand how many people we needed. And as well, we had equipment with long lead times. So the two main pieces of equipment that we needed to plan for were lifts. So if you think of a mechanic shop, you need to lift the car up so you can work underneath it, and then as well so that you can change the tires, work on brakes, and then the paint. In the body shop, you need to have paint booths, and this is where you could paint and cure paint on a vehicle. So as you all know, the business analytical tool of choice is Microsoft Excel, right? So we started building these models in Excel, bringing in data, and initially we could answer these questions, right? Site X was going to have 100% increase in demand. Can we meet the challenges, right? We could go through the Excel modeling process and answer these questions. But as the volume of questions increased and the complexity of the questions increased, Excel broke, right? As you know, Excel is not really a scalable solution, not reliable, doesn't have real-time information within it. So we're looking at alternatives, right? we had two alternatives that we were considering. One is going with a consulting company. So we had consulting partners that said that they could build this, right? They had development teams, they could have a front-end, back-end team, build a custom software solution. Problem with that, as you all know, is it's very costly to go with consultants. And secondly, it would take a lot of time and energy to integrate with our existing systems. And then secondly, we could buy an existing capacity supply chain software solution. But due to the unique nature of our operation, a lot of these software solutions were built with the manufacturing operation in mind, right? So it would take heavy customization, a lot of time, and a lot of money. And these were things we did not have. We did not have a ton of money up front. We didn't have a lot of time. We needed to answer these questions quickly, as you all may have problems. So what we started doing is migrating off of Excel and building it into Python, right? We were using Excel and Alteryx to update our data, build our models. That wasn't working. We started migrating into Python so we could increase the velocity and speed and complexity of the questions we were answering. And the next step to that was considering how do we visualize this and make this interactive, right? And in the Python space, like you've got a number of different dashboarding, web framework libraries out there, but the one we knew of and that was most popular, most customizable was Dash. So we started building a proof of concept in Dash open source, and I'll get into a little bit more why. So we started going to Dash Enterprise. We started going to Dash open source, and we weren't able to fulfill all the customer demands. So in terms of two aspects. One is security. As many enterprises have concerns about security. We were using the open source software. I was managing authentication. It wasn't a great experience. We needed to upgrade and have a path so that we can integrate with our existing security tools like Okta and our own authentication. And then secondly, we needed the application to look and feel like other data applications that we had within our portfolio so that it could increase trust and user adoption across our 50+ sites and corporate leadership. To accelerate this, we decided to upgrade to go from Dash open source to Dash Enterprise. One, it was like fairly seamless, and secondly, we were able to fulfill the requirements of the theming and branding and as well the security. Just kind of double clicking on why Plotly and Dash. As many of you know Plotly Express, Dash, a lot of downloads, 16 million plus downloads per month of Plotly visualization libraries, 2+ million downloads per month of Dash, a lot of GitHub stars, so it's really well known. It's not some software company that's gonna go away next year. And that's why we decided that we should, because of not just the trust in the community, but also the customization and the flexibility of Dash, we decided to go down that path to build this internal data application. So going into more of why Dash Enterprise and Plotly Professional Services, we were a small team, right? I had a team of myself and one other industrial engineer. We weren't professional software engineers, we weren't Python developers, kind of data scientists, right? So we needed some help. So we were canvassing our other partners. We had other consulting partners that would offer up Python developers, but they really didn't have the expertise in Dash and really wanted to go down the path of Dash versus using Angular, React, or other front-end libraries. So we decided to start incrementally investing in a relationship with Plotly Professional Services. Plotly is the company behind Dash, and they've got a small, great team of developers that understand the Dash Enterprise library. They build apps day in, day out, so they could accelerate our development of these tools, and then secondly, they bring along development best practices. Like I talked about, we weren't professional developers. We needed to learn some best practices like CI/CD, code reviews, app testing, committing code into repos. And then lastly, this team was very experienced with UI, UX, and branding applications to fit corporate styling guides. So we were able to work with the Plotly Professional Service team and our team and our UI, UX team to ensure that the application looked and felt like other internal tools. It didn't look like some generic web application that people couldn't trust, right? It looked like our other internal apps. So this is a GIF of one of two main pages. So this is the multi-site view. So this view was built with two main users in mind, our corporate and our regional leaders. And with our corporate and regional leaders, what they really needed to do was, at a slice of time, be able to see demand and supply and capacity across multiple auctions at a time. So here we're selecting a time frame. So this is April 2023. We're selecting my region. We're in Georgia, so we're in the southeast. And as you can see, it's pretty quick, but you can see red, yellow, green. At a quick snapshot, you can look, hey, in my region, these auctions we have concerns about. I need to double click on them. Or these auctions are green. Maybe we need to bring in more demand or shift demand, right? And you can also click on all auctions. So as you can see here, 2 points here. One is the speed. Like you can see that as we click and as we change things, models rerun, things regenerate. So it's very fast, it's real time. And secondly, it's on brand with our other internal data applications. We've got, as you can see on the left-hand corner, the little M, that's the Manheim brand. The colors match, the look and feel match other applications that we use internally. The next slide I'm going to show is our single site application, and this is the last of the two main pages in our application. And this is what's built for two main purposes. One is for a site's users and leaders, from the general manager on down, to be able to really see that capacity over time at their site. And secondly, it was built to be able to do scenario planning. And the way we define scenario planning is we feed the model with good defaults of data and demand and forecasts, but with scenario planning, you can change this. So in here, you can see that you've got some data cards showing data and graphs on like how we're doing in terms of capacity. If you click on scenario planning, there's a number of different inputs we can change. In this specific use case, they're changing proficiency. So proficiency is a term very specific to the auto industry, but it's a measure of the efficiency of how efficiently a technician can convert their own hours into billable hours. So if you've ever gone to a dealership or mechanic shop, you may be billed hours. These are like industry standard terms, right? Like if you get billed 2 hours, if a technician can do that 2 hours in 1 hour, they're 200% proficient, right? So in this case, they're increasing their proficiency. So in this fictitious example, we're investing heavily in IT and process improvement so that they can be more efficient. And as they do so, it changes the amount of capacity available to bring in new demand. So this is just one instance where we can show that scenario planning is very useful as things are very dynamic and change. So that was very useful for two main purposes. Right? One is to be able to, in real time, see changes in a situation, and you can model that. And secondly, be able to do that, be able to change inputs and see the output and increased user adoption and trust, because people could link the input with the modeling that we conducted mathematically with their understanding, and they could trust the outputs because they saw in real time and with their own inputs how that changed the outputs. So these are the last two main content slides. I have 6 main points of how we demonstrated a return on investment in terms of the funds and time that our leaders provided our team to be able to invest in this application. The first one is really, as I'll reiterate, we could accelerate a proof of concept into an application quickly and with a low investment of money. Secondly, security compliance. We can meet the requirements of our IT product organization regarding authentication and security. It all integrated with our current existing tools so that we had confidence that our application and the data and the models would not get out to our bad actors. Our third point, lowered barriers to use the application. Unlike Excel or other applications that we may have considered, this application is branded, it's styled, and the look and feel of it is very consistent with our other applications, and it's very easy to use. So that helped non-technical business users to be able to use the application and gain trust and increase adoption. So last 3 points. The fourth is back-end pipeline support. So this dovetails in with Python and Dash Enterprise. So previously, like I talked about before, we were using Excel plus Alteryx to pull in data and update the data. Due to the laborious nature of that process, we're updating data, say, every week, every month. But with Python and with Dash Enterprise, we're able to update, say, in minutes or in hours, pulling from our on-premise databases, from Snowflake, our data warehouse, being able to do an ETL process, quickly aggregate the data, push it back into Snowflake, and then in Dash Enterprise, we've got a process where we can rehydrate our data, pushing into Redis and Postgres so that we can, one, be performant so that we're not tied up in network calls, getting data across the network. And secondly, any issues with like disasters or communications issues, if the database goes down, the application will still be up because we've got that built into the Dash Enterprise server. Fifthly, we can avoid full stack costs, right? In Dash Enterprise, we built the application primarily all in Python. We didn't need to learn a front-end language. We didn't need to hire front-end people. We did it all in Python. It's very performant, and it works well. And lastly, it's multi-page and branded. So the multi-page aspect of this application was really helpful so that we could answer different questions across our business that specific users may have, and we can all have it within the same application. And secondly, it's branded so people can trust and understand how to use the application because it's very similar to other applications that we have internally. This is the last slide. Just to reiterate, we had a problem planning equipment and labor across our 50-plus auto auction sites. And we turned to Python and Dash Enterprise and the Plotly Professional Services team to be able to help us accelerate the development of an application and a process to answer the questions that our business has. That's the end of my presentation. I think we may have a couple minutes for questions. If anyone has questions, they could just stand up. This gentleman first, and then the gentleman. Yep. Yeah. So I'll reiterate the question if you couldn't hear. The question is, when we moved from Dash open source to Dash Enterprise, why did we do that? And why did we do so? And what were the key features that led us to do so? So I think the two main features that we talked about, and there's other features as well. One is security. You've got built-in integration with the existing authentication and software, security software already out there. So for us, we use Okta. It integrates very seamlessly with Okta, so that we can ensure that everyone who's authenticated within our network can use the Dash Enterprise as long as they're provisioned. And secondly, the theming aspect. There's specific Dash Enterprise libraries, Dash Design Kit, that allows us to theme very easily and seamlessly so that the application can be on brand. This gentleman here. Yeah, so the question is, were the GIFs and the animations, were they all made in Plotly and Dash Enterprise? So yes, those GIFs, they were all, they're videos of the application live working on the web as we click and as we change inputs. There's this idea of like, again, a little technical, but it's called the callback. So an input is changed, it runs a callback, it reruns models, and it shows the output again on the website. That's a great question. The question is, how did we improve performance of the application versus, say, like Tableau, Power BI using Dash, right? I think the key feature that led us to go to Dash open source and Dash Enterprise is this idea of being able to use callbacks and be able to rerun Python models in the back end. So you change an input, and you can run a whole series of models that are invisible to the user, but run very quickly in Python, mathematical models, and regenerate outputs, right? It's very difficult to do that in Power BI and Tableau. And then as well, secondly, because you're writing this all in Python, you can customize the application so it looks and feels and operates in a manner that you're not constrained by these GUI-based tools like Tableau and Power BI. I think I have time for one question if there's any more questions. This is the gentleman in the back. So I think the question is, what stops a user from like gaming the system and the application because they see the scenario inputs, right? So I think the key point there is there are defaults generated in our system based on the data that's coming in, that's generated like historical averages of demand and usage of equipment and labor by person and by client. They can change that and change the output, and they can generate a report. But really, if they've got key decisions to make, the leaders know that they can walk through these inputs and see the defaults and see them change it. And because it's so fast, you can reset them to defaults and then change the input again. So because of the speed and the ease of changing back to the default, you can see any input changes and how that changes the output. And those inputs that you're changing in scenario planning, they're not going to change the defaults for all users, right? It's a stateless application. Oh. Oh, interesting. So this is an operational question, right? Like if you work faster, quality may decrease, right? Like that gets into the weeds of like the modeling of how fast we can say people can work, right? And we work with the industrial engineering team and then some of our operational excellence team members to mathematically model this to be able to put in good defaults for sustainable rates of production long-term across different auctions and by clients, right? So we don't want to just push our people to work harder and reduce quality, right? Like there is, as one of the inputs, we do have quality as one of the metrics in there, and we have quality that we are starting to measure and have as an input because we know that as quality decreases, actually production decreases, right? Because you've got rework coming in, right? I think that's all the time I have. I'll be around in the back or at the Plotly booth after this. Thank you all for the time. Appreciate it.